Alright, kinetic energy was the topic of our last video. In this one we are going to be talking about work and how work ties back into kinetic energy. So the question comes up, what is work? By definition, work is energy that is either transferred into or out of the system. So when I talk about work, I often talk about it with the cookie jar approach. We either do work and add energy into the system, or we do work and remove energy from the system. So we kind of have this whole cookie jar approach of either we're adding energy or cookies into the cookie jar, or we're taking them out of the cookie jar. So how does work transfer energy into and out of the system? What it does is it transfers this energy by means of a force. And this force is acting on the object. Now, typically when we say we're transferring energy into the system, we call that positive work. And when we're taking energy out of the system, we're calling that negative work because we're decreasing the energy in that system. Now, you may want to know, how is work and energy connected? Now, what we could do is we could look at a piece of string and at a bead that is traveling along that string. So the bead has some initial velocity that gives us an initial kinetic energy, and we have a force that's pulling on that bead at some angle phi from that horizontal string. That string is in the positive x-axis. So at some point later, further down the string, we have a new velocity, and that gives us a new kinetic energy, what we're going to call our kinetic final. And so the question is, what has happened in order for us to arrive at that final kinetic energy? Now, we know that we have an initial velocity v initial here. We have a final velocity v final here. We have an acceleration based on that force, and we have some distance that this bead has traveled. So we can actually look at our basic, one of our fundamental kinematics, v squared equals v naught squared plus 2a change in x, which in this case would be our distance. Now from this we could solve for our acceleration. We know our acceleration is based off this force, so we know that the net force in the x direction is going to equal mass times the acceleration in the x direction. So that's going to help us find out first what our acceleration is here. So we have v squared minus v naught squared is going to equal 2a times our distance d. If we divide by 2d on both sides, what we're going to get is that our acceleration in the x direction is going to be v squared minus v naught squared over 2d. If we bring that over here and we put that in here for the acceleration, what we're going to have is that the net force is going to equal the mass times v squared minus v naught squared over 2d. That's going to be our force in the x direction. If we multiply by d, we're going to get that the force in the x direction times the distance traveled is going to equal 1/2 mv squared minus 1/2 mv initial squared. Well, this is the kinetic final. This is the kinetic initial, so that's the change in kinetic energy. And that's going to equal the force in the x direction and the distance that was traveled in the x direction multiplied together. This is the work done by that force. So in order to have work being done, you must go a distance. If you go no distance, there is no work. So this work represents the change in the kinetic energy of the system. So the change in the energy of the system, which is work. So work is equal to the change in kinetic energy. Now this is a very important principle. Work, kinetic energy theorem. That is a very important concept. You will be using this time and time again. This will become one of your new best friends when you're solving problems on the homework. That work is equal to the change in kinetic energy. You may have a piece missing here. You may not know the final kinetic energy. You may not know the initial kinetic energy. But if you pay attention to your context clues, things start working out clearly. So what we got is that the work done by a constant force is equal to the force times the distance that it's traveled in that same direction, cosine of the angle between the force and the distance. So in the last example we had the bead, the string it moved along, and the force was applied up at some angle. So we have the distance we moved and the force, so we're looking at the force magnitude times the distance magnitude, cosine of that. Well, that's just the dot product definition. So if we take the force vector and dot it with the distance vector, that gives us the work that is done by a constant force. Now the force must be constant here. That means that you cannot change magnitude, cannot change direction. Force must be constant in order to use this definition. Okay, so let's look at an example. We have SPY 001 and SPY 002 trying to move a 225 kilogram safe, and they're trying to move it across the floor a distance of 8.5 meters towards their truck that's waiting for them. Okay, so SPY 1 is pushing downward, 30 degrees downward, on the safe with a force of 12 newtons. This is 30 degrees. SPY 2 is going to be pulling upward 10 newtons at an angle of 40 degrees on the safe. So the safe is going to have several forces. It's going to have a force from SPY 1. We're going to have a force from SPY 2. We're going to have a force due to gravity and a force normal because it is sitting on a surface. Now, these are not necessarily drawn to scale. So, what we know that obviously the box isn't rising off the pavement, and obviously it's not sinking in, so we know that the net force acting on the box in the y direction should sum to 0. So what forces do we have in the y direction? We have force normal. We have the y component of SPY 2 upward. We have the y component of SPY 1 downward. And we have force due to gravity. Now that should all sum to 0. So now if the surface is frictionless, can we determine what the work is that is done by SPY 1 and what the work is that is done by SPY 2? Well, the easiest way to do that is to use the dot product definition. Force dotted with the distance. Keep in mind those have to be vectors. And that dot product gives us a scalar result. So SPY 1 had a force magnitude of 12 newtons. The distance that was traveled was 8.5 meters to the truck. This is going to be cosine of 30 degrees. So it's 30 degrees from the horizontal. So this is going to give us about 88.3 joules. Now if we look at SPY 2, their work is going to be the force, which is 10 newtons, times the distance, which is 8.5, times cosine of 40 degrees. Now that's going to be about 65.1 joules. So we can find the work done by both of them. Can we find the total work that is being done on the box? Well, yeah, all we have to do is just add work 1 and work 2. So the work done by each of those spies. And what we're going to get is that it's going to be about 153.4 joules. So that's the total work on the box. That's the energy we're putting in the system to move that safe all the way up and into the truck. Now there's something that we've kind of neglected to mention here. These two forces, force 1 and force 2, exert work. But what about force normal and force due to gravity? Well, they're perpendicular to the direction of travel. So the work done by the force due to gravity is going to actually be the force due to gravity dotted with the distance. That angle is 90 degrees. That's going to be 0. So any force that is perpendicular to the direction of travel does no work. You have to have a component parallel to the direction of travel in order to have any work done on the system. So can we find the final velocity of the safe? Well, we know the final work that's done on the system, so we know that the energy of the safe is increased by this much. What else do we know about the safe? Well, most safes are stationary, so the safe should have been initially at rest. So if we use that work is equal to the change in kinetic energy, what we get is that the final kinetic energy minus 0 is going to equal this 153.4. So our kinetic final, which is 1/2 the mass, which is 225, times the velocity squared, is going to equal 153.4. So we multiply by 2, we divide by 225, and we are going to get that after we take the square root, velocity is about 1.17 meters per second. So it's going just over a meter every second to gradually get its way out to the truck. It's actually a pretty quick pace considering the size of the safe. So we're going to end our discussion on work here for today. Next time we will pick up on work done by the gravitational force.